Okay, this is section 6.5, which covers work. And by the way, this is the last section of Calculus 1, so yay for us. This will probably be composed of 2 videos. So this is going to be the first video of a 2-part series. And we're going to talk about work. So before we start using the work formula, we have to define what a force is. So a force is a push or pull on an object, and the units are in newtons or in pounds. So if you're using standard units, you're going to talk about newtons, and if you're using the American units, those are going to be in pounds. Therefore, work is done when a force acts on an object and it moves. So we see this formula here. It says work equals force times distance. Okay, so the units for work are going to be in joules, which are Newton meters, feet per pound, inches per pound. So once again, these two are going to be the American units, and the joules is going to be the standard units. And so let's look at the first example, which actually is pretty easy because it is work done by a constant force. So once again, we use this formula here. So example 1 says, find the work done for each force. You push a chair 30 meters with a constant force of 90 newtons. How much work is done? So we know we're going to use the formula work equals force times distance. The distance in this particular case is 30 meters, and the constant force of 90 newtons is force. So work equals 90 newtons times the distance of 30 meters. So what we're going to do is we're going to multiply these two together, and what we get is 270 newton meters, which we can call that joules. So 270 joules, and I'm missing a 0 there. So let me rewrite this so it's a little bit cleaner, but it's going to be 2,700 newton meters, or 2,700 joules. Okay. So part B says you lift a 50-pound box 4 feet. How much work is done? So you lift a 50-pound box. 4 feet is going to be the distance, and the force is lifting that 50-pound box. Okay, so this is a force. So once again, work equals force times distance. So 50 pounds, and we're moving that a distance of 4 feet. So 4 times 50 is going to give us 200 feet pounds. Okay, so that's how we do constant force. Now let's look at variable force. So part B talks about how we handle this. So once again, just like everything else, when it varies, we're going to have to use integration. So the work formula is defined as integrating from a to b, f of x dx. By the way, if you're moving something back and forth, it's dx. If you're moving something up and down, it's going to be dy. So in this particular case, we're moving an object, left to right. So that's why our integration is x equals a to x equals b, and we're using the dx. So let's go ahead and look at example number 2. So we know we have to use the work formula, and we know we're going to integrate from the lower limit to the upper limit, f at x dx. So when we read this, it says example 2, a variable force of f of x equals x squared plus 1 pounds moves on an object from x equals 0 feet to x equals 3 feet. How much work is done? So if we fill in the gaps, we're going to integrate from 0 to 3. F of x is x squared plus 1 dx. And now we have to integrate. Okay? So if we integrate x squared, we get 1/3 x cubed. And if we integrate the value of 1, we get x. And remember, we're integrating this from 0 to 3. So the next thing I have to do is I have to take f at b minus f at a. So f of b looks like this, 1/3 times 3 cubed plus 3 minus 1/3 times 0 cubed plus 0. Okay. 3 cubed, by the way, will give me the value of 27 over 3 plus 3. And then the rest of this stuff is going to zero out. So 27 divided by 3 gives me a 9, and 9 plus 3 is going to give me 12. And remember, this is in feet, pounds. Okay? All right, so that's example number 2. So that one's not too bad. Let's look at the example number 3. Before we do, we have to talk about what Hooke's law is. So we're going to talk about variable force when we deal with springs. So Hooke's law states the force required to stretch a spring x units past its natural length is proportional to x. So f of x equals kx, where k is the spring constant. Okay, so for example 3, it says a spring has a natural length of 2 meters. A force of 6 newtons stretches the spring 2 meters past its natural length. For part A, find the spring constant. Okay, so we know the formula says f of x equals kx. All right, and it goes on to tell us that we have a force, and we know the force is 6 newtons, and it equals k times x. X is going to be our natural length, which is 2. Okay, so k equals 6 divided by 2, or k equals 3. So now you have your constant, and by the way, this constant is in Newton meters, or newtons per meter, excuse me. So that's part A. All right, so let me go ahead and highlight that just so we know we found the answer. And let's look at part B. Find the amount of work done in stretching the spring to 6 meters. Okay, so work equals the integration from lower to the upper limit of the function dx. Okay, so we got to figure out what the limits of integration are. And we know that the starting point is a spring has a natural length of 2 meters, and then it ends when it stretches the spring to 6 meters. That's what it says in part B, right? So if we let 0 equal where it starts, then 6 minus 2 is 4 is going to be where it ends. So when I integrate for part B, I'm going to do 0 to 4. The function f of x is going to be and I didn't do this here, but it's going to be really easy. So f of x equals kx, and we know k is now 3. So f of x is 3x. So I'm going to go ahead and throw that 3x in there, dx, and once again I get that 3x by using the constant that we found, the spring constant times x. Okay, time to integrate. So if I integrate this, 3x becomes 3/2 x squared. And remember, we're going to integrate this from 0 to 4. So now I have to do f at b minus f at a. So f at b becomes 3/2 times 4 squared minus f at a becomes 3/2 times 0 squared. So basically I just have to worry about the first one. 4 squared is 16. And 16 times 3 is going to give me 48. Or excuse me, I made a mistake there. It's 24. Because it's 48 and then I divided by 2. That's how I get 24. And then I'm going to subtract 0 from that. So once again, 4 squared is 16. 16 times 3 is 48. 48 divided by 2 is 24. So my answer is going to be 24 joules. Or remember, that's Newton meters. Okay? All right, let's do part C, find the work done if compressing the spring the first half meter. Okay, so for this one, the limits of integration, if we start, where it's 2 meters past the stretching point, remember that's 0, or 2 meters is a normal stretch. And then they say they want us to go to a half a meter above that. So the lower limit is going to be 0, and the upper limit is going to be 1/2. Okay, because it said stretch it 1/2 meters past that. Okay, so I set up my integration. So remember, work equals integration from the lower limit to the upper limit, f of x dx. Okay, so if I plug in the values, I integrate from 0 to 1/2, or you can use 0.5, whatever you want to use. And then remember, the function is 3x dx. Okay, all right, so we're going to integrate that. So if we integrate that, it becomes 3/2 x squared. And we're integrating that from 0 to 0.5. Okay? All right, in this case, because I have fractions, I'm just going to make this 1/2. You can use what you want. And now all I have to do is take f at b minus f at a. So f at b is going to look like this: 3/2 times 1/2 squared minus 3/2 times 0 squared. Okay, so we know that f at a is going to 0 out. If I square 1/2, I get 1/4, and I'm going to multiply that by 3/2. And that equals 3/8. And if you divide 3/8, if you want the decimal, it's going to be 0.375. And remember, this is in joules. All right, so that's part C, and we have one more part for this video. Part D states, find the work done in compressing the spring the second half meter. So once again, we're going to use this formula, work equals lower to upper integration of f of x dx. Okay, so the lower limit is going to be 1/2, and the upper limit is going to be 1. So the lower limit is 1/2, and the upper limit is 1, because it basically stated that in the question, the work done in compressing the spring the second half meter. Okay? All right, so we're going to fill this out. So work equals 1/2 to 1 of 3x dx. Okay? And I know we've integrated 3x several times. We know that's going to give me 3/2 x squared. And we're integrating that from 1/2 to 1. Now, I have to take f at b minus f at a. Okay, so f at b is going to be 3/2 times 1 squared. And f at a is going to be 3/2 times 1/2 squared. Okay, so I know f at b is going to give me 3/2. And then minus, I just figured out what 3/2 times 1/2 squared is. And remember, we got 3/8. Okay, so if we find a common denominator of 8, 2 goes into 8 4 times, and 3 times 4 is 12. So 12 minus 3 is going to give me 9/8. Okay, so 9/8 in decimal form is 1.125, and once again, we're in joules. So that's how you figure out how to do part D. All right, so that is going to be the end of the first video, and you know, definitely watch the second video so you can fill out the last 2 pages.